All right, let's dive in. We're going deep on cybersecurity today. 29 brand new publications from Arxiv, all about the latest in cybersecurity research.
Wow, yeah, that's a lot to unpack.
It is, but it's exciting stuff. We've got everything from like AI-powered malware detection to some really sneaky new cheating tactics in online gaming.
I know, right? It seems like every time we turn around, there's a new threat or vulnerability popping up.
It's a constant cat and mouse game, isn't it?
Absolutely. But that's what makes this field so fascinating. There's always something new to learn and new challenges to tackle.
For sure. Okay, so let's jump right in with something that I think will grab the attention of any gamers listening. Have you heard about this new thing called VIC?
VIC.
Yeah, it stands for Virtual Machine Introspection Cheating.
Oh, right. Yeah, I read about that. It's wild.
It's insane. Basically, they're using virtual machines to hide cheats from anti-cheat systems.
Pretty clever, right?
It is, but also kind of scary. Imagine what could happen if this becomes widespread.
I know. Like cheating as a service powered by cloud infrastructure.
Exactly. It could completely change the landscape of online gaming.
No doubt, developers are going to have their work cut out for them trying to stay ahead of this.
Speaking of staying ahead, let's talk about LLMs.
Large language models, yeah.
Right, everyone's talking about them these days, ChatGPT, Bard, all that. But what really caught my eye is how they can be used for both good and bad when it comes to security.
Totally. There's so much potential there, but also a lot of risk.
Okay, so on the one hand, you've got researchers developing tools that use LLMs to translate like natural language access control policies into machine enforceable ones.
Right, like LMN. That could really simplify security implementations, making them more accessible.
Exactly. But then on the flip side, there's the potential for LLMs to be exploited, through things like prompt leakage attacks or even backdoors being implanted into LLM-based agents.
Yeah, those are some serious concerns. It's almost like a double-edged sword.
It is, and it just goes to show that we need to be really careful about how we develop and deploy these technologies. Okay, moving on, let's talk about the battle against machine-generated text, MGT.
Yeah, that's a hot topic right now.
Researchers are constantly developing new attack methods and defenses for these MGT detectors. It's like an arms race.
Totally. What I find interesting is how researchers are using adversarial training techniques to create these more robust MGT detectors.
Right, I know. They're training them to recognize these subtle patterns and variations that might indicate that the text is machine-generated.
Like teaching a detective to spot a forgery. I love that analogy.
It's a good one, right? And then there's trend, which is a whole other approach. It hides information within text by replacing normal white space with, like, visually similar Unicode characters.
Yeah, it's a very clever technique. Kind of sneaky.
It is. It highlights the need for out-of-the-box thinking in cybersecurity, right?
For sure. You can't always rely on traditional methods. Sometimes you got to get creative.
Absolutely. Okay, enough about software for a bit. Let's dive into some hardware.
Okay. Like what?
DRAM.
RAM, what about it?
It turns out that even this fundamental component of computer memory is susceptible to errors. These read disturbance errors.
Right. Those can happen when certain memory locations are repeatedly accessed.
Exactly. And that can corrupt data or even crash the system.
Yeah, that's a big problem.
It is. And while there are mitigation methods like partial row access control or PRAC, those can have some pretty significant performance overheads.
Especially with future denser DRAM chips, right?
Right, but that's where this new technique, Cronus, comes in.
Cronus?
Yeah, it addresses the weaknesses of PRAC and has like near zero performance overhead. It's pretty impressive.
Oh, wow. That does sound promising.
It does, but then there's this other thing, variable read disturbance, or VRD.
VRD.
Yeah, it makes DRAM security even more challenging because the DRAM row's susceptibility to errors can actually change over time.
Oh, so it's not static.
Exactly. So yeah, DRAM security is a whole other ballgame.
It really is. It seems like everything is connected, You fix one problem and then another one pops up.
It's true. It's a never-ending cycle. All right, let's shift gears again and talk about federated learning. It's this decentralized approach to training machine learning model that, on the surface, sounds great.
It does, but like anything else, it has its vulnerabilities.
Exactly. And one of the most interesting attacks is this thing called the Pike attack.
The Pike attack, what is that?
It manipulates item embeddings to promote specific items, but it doesn't even need prior knowledge of the model.
Really? How does that work?
Well, it targets popular item embeddings and subtly shifts them to promote these targeted items. Like, imagine an attacker using this to manipulate, product recommendations on a shopping site.
Oh, that's sneaky and scary.
Right. It's a reminder that even when we try to decentralize and distribute learning, there are still vulnerabilities that can emerge. Fortunately, researchers are already working on new regularization techniques to counter these attacks.
That's good to hear. So are we, like, winning the battle against these attacks?
It's hard to say. It's a constant back and forth. But one thing is, for sure, the research in this area is incredibly important.
Agreed. Okay, what else have you got?
There's a lot of debate around whether training with synthetic data actually protects privacy.
Right. I've read a bit about that. Seems like it's not a simple yes or no answer.
It isn't. Studies are showing that different methods of generating synthetic data offer varying levels of privacy preservation. So even when real data is removed from the equation, there are still privacy risks to consider.
That makes sense. So synthetic data isn't a silver bullet.
It's not, but it's definitely a valuable tool that needs to be used carefully.
Right. Man, cybersecurity is such a complex field.
It is. We've only scratched the surface of what these 29 publications have to offer.
I know, right? What else is there? I'm hooked. There's just so much cool stuff happening in cybersecurity research these days. One area that I find particularly interesting is this new work on secure key leasing.
Key leasing.
Yeah. Basically, it's a way to share cryptographic keys, but only temporarily. And you can revoke them if you need to.
Oh, like giving someone a key to your house, but with the ability to change the locks later.
Exactly. That's a perfect analogy. And these new key leasing schemes are really cool because they're based on simpler assumptions than previous methods.
Simpler. What do you mean by that?
Well, like they rely on the existence of one-way functions or the hardness of the SIS problem. These are well-established concepts in cryptography.
Okay. So they're built on solid foundations. But what about their security? Can you really revoke these keys effectively?
Absolutely. That's one of the big advantages. They offer classical revocation, meaning you don't need a quantum computer to revoke the keys.
That's a big deal, right? Because some of the previous schemes relied on quantum revocation, which isn't very practical.
Exactly. Plus, these new schemes offer enhanced security guarantees.
Enhanced. In what way?
Well, for example, imagine a scenario where the verification key for revocation gets leaked. Like, after the adversary has already submitted a valid certificate of deletion.
Oh, that sounds bad.
It would be disastrous in prior constructions. The system would be totally compromised. But these new schemes are designed to withstand that. Even if the key is leaked, the system remains secure.
Wow, that's impressive. So it's like having a backup security system in place, just in case.
Exactly. So yeah, these new key leasing schemes are a big step forward in cryptography.
They sound like it. It makes you wonder, though, with all this talk of enhanced security and classical revocation, what about quantum computers? Aren't they going to change everything?
That's a great question. And it brings us to the world of quantum sieving algorithms.
Quantum sieving.
Yeah, they're these algorithms that are specifically designed to attack lattice-based cryptography. They leverage the power of quantum computers to try and, like, crack the codes that protect our online transactions, communications, all that stuff.
So quantum computers versus our current encryption methods. Sounds like a battle for the ages.
It is. And to really understand what's at stake here, researchers have been analyzing how much resources it would take to implement these quantum sieving algorithms. They've looked at things like, quantum arithmetic operations, quantum random access memory, all those details. And what's interesting is, even with some pretty optimistic assumptions about quantum computing advancements, cracking the codes used in lattice-based cryptography is still a monumental task.
So are you saying we're safe?
Not exactly safe, but we definitely have some breathing room. I mean, we're talking needing a ridiculous amount of resources to solve the shortest vector problem on a lattice of dimension 400. Like something on the order of 10 to the 13th power physical qubits and 10 to the 31st power years.
Wow. That's a long time.
It is a really, really long time.
So it sounds like we don't need to panic just yet.
Not quite. It's important to stay vigilant and keep investing in research on both quantum-resistant algorithms and defenses against these quantum attacks.
Right, of course. It's like a constant arms race. Speaking of which, let's talk about neural networks. They're great for all sorts of things, but they're also vulnerable to attacks, right?
They are, yeah. Like convolutional perturbations which can disrupt the input data and cause errors.
And those errors can have real-world consequences.
Absolutely. Think about a self-driving car misinterpreting a stop sign because of a tiny distortion in the image from its camera.
Yeah, that's a scary thought. But thankfully, researchers are developing ways to verify the robustness of these neural networks against these kinds of perturbations.
Right. One approach is using parameterized kernels, which are these mathematical functions that can represent various distortions, like blurring or camera shake. And by, appending a linear layer to the neural network that encodes these kernels, researchers can get these tight bounds and high effectiveness in the verification process.
So they're basically giving the neural networks a way to see through these distortions.
Yeah, that's a good way to put it. It's pretty cool stuff.
It is. Okay, so we've talked about quantum computers, neural networks. What else is there?
Well, this might seem a bit old school, but denial of service or DOS attacks attacks are still a big problem.
Yeah, I remember learning about those back in like Intro to Cybersecurity.
Right. But the thing is, attackers are always finding new ways to launch these attacks. And what really caught my eye is this new type of DOS attack that targets large language models.
LLMs again?
Yep, researchers are calling it CRABs. It stands for Consuming Resource via Auto Generation for LLM DOS attack.
Crabs, that's a catchy name.
It is, and what makes these attacks so dangerous is that they're not just about flooding a server with random requests. They use these auto-generation techniques to create these complex prompts that force the LLM to work overtime.
So it's like giving the LLM a ton of homework that it can't handle.
Exactly. And the worst part is that CRABs can operate in black box settings, so the attacker doesn't even need to know the LLM's internal workings to launch the attack.
That's not good. So how do we defend against these crabs attacks?
Well, researchers are exploring a few different strategies like rate limiting, input validation, and anomaly detection. It's all about trying to identify these malicious requests and block them before they can do any damage.
Makes sense. So it's all about protecting the LLM from being overwhelmed. Okay, before we wrap up, there's one more thing I wanted to touch on. Using graph neural networks for cyber defense. I've heard some buzz about this, but I'm not really sure how it works.
Oh yeah, graph neural networks are super cool. So you know how traditional cyber defense systems often rely on these predefined rules and signatures to detect threats?
Yeah.
Well, those systems can struggle to keep up as attacks become more sophisticated. But graph neural networks, they can actually learn complex patterns and relationships from network data, so they can identify both known and unknown threats much more effectively.
Oh, I see. It's like having a security guard who can not only recognize familiar faces, but also spot suspicious behavior patterns, even if they've never seen them before.
Exactly. And researchers are using these graph attention networks, or GATs, which can process all these different features of the network, like node, edge, and global features. They're combining that with reinforcement learning techniques, so the system actually learns the best defense strategies through trial and error.
So it's like giving the security guards some training simulations where they can practice different tactics and figure out what works best.
Yep, exactly. And what's really impressive is that these GAT-based defense systems can adapt to changes in the network, so they can still work effectively even if new devices are added or removed.
So they're not just learning to recognize threats, they're also learning to adapt to changes in their environment. That's amazing.
It is, and they can even generalize to networks of different sizes, which is pretty cool.
So you're telling me that these graph neural networks are the future of cyber defense?
Well, they definitely have a lot of potential, but, there are still some challenges to overcome, like the computational cost of training these networks.
Right, there's always a catch.
Always. But researchers are working on ways to make them more efficient, so I'm optimistic.
Me too. This is all really fascinating. What else is there? It's mind-blowing to think about these graph neural networks constantly learning and adapting to protect against cyber threats, like a digital immune system. But with all this AI stuff and advanced algorithms, what about the ethical side of things? Using such powerful tools for cybersecurity, that's got to come with some responsibility, right?
Oh, absolutely. We have to be super careful as we develop these increasingly sophisticated systems. Because think about it. What happens if a graph neural network is trained on biased data?
Oh, yeah, I see what you mean. Could it perpetuate those biases, like in its decision-making, leading to some unfair outcomes?
Exactly. It's like that old saying, garbage in, garbage out. Even the most advanced AI is only as good as the data it's trained on. So the question is, how do we make sure these systems are fair and unbiased?
Right. How do we fix that?
Well, that's where this concept of machine unlearning comes in. It's all about developing techniques to remove the influence of specific data points from a model that's already been trained.
Oh, interesting. So it's like hitting the undo button on the learning process, right? So you can correct mistakes or adapt to new standards.
Exactly. It's like teaching AI to forget, which sounds kind of weird, but it's important.
It does sound a little counterintuitive. So how does that work, machine unlearning?
There are a few different approaches. Some methods, like naive retraining, involve retraining the entire model from scratch on a new data set. That's straightforward, but can be super computationally expensive, especially for large models.
So it's like starting over with a clean slate. Not very efficient. Are there other ways to do it that are maybe more efficient?
Yeah, there's this thing called exact unlearning, which tries to remove the influence of specific data points without retraining the whole model. It can be more efficient, but it often needs more complex algorithms.
So it's a trade-off, right? Efficiency versus precision. But this whole idea of machine unlearning is fascinating. We're basically teaching AI how to forget.
I know, right? It's like we're trying to control how AI learns and adapts, making it more responsible, and researchers are working on making it even more practical, applying it to more models and situations. One promising area is integrating unlearning principles into positive unlabeled learning.
Positive unlabeled learning, what's that?
So it's where you have these data sets where only some data points are actually labeled, and they're trying to figure out how to do unlearning in those scenarios, which is really tricky.
It sounds like trying to unlearn something when you only have partial information about what you learned in the first place.
Exactly. It's a tough problem, but if they can figure it out, it could be a game changer for data privacy and AI ethics.
I see what you mean. So it's not just about developing powerful AI, it's about making sure it's used responsibly and ethically.
Exactly. That's the key.
This has been a wild ride. We've covered so much ground today, everything from sneaky cheats in video games to quantum computers and the ethics of AI. It's clear that cybersecurity is a constantly evolving field.
It definitely is. And it just goes to show how important research is. Because the more we understand about these threats and vulnerabilities, the better we can defend against them.
Absolutely. Well, that's a wrap for this episode of The Deep Dive. Thanks for joining us.
It's been a pleasure.